Okay, so good afternoon. I'm Henry. I'm a PhD student with Fung, and I will present this result on improved provable reduction of NTRU and hypercubic lattices. So this is a bit of a technical slide to start with, just to summarize the results. Sorry, we have this bit on the side. So the motivating question is it possible to show that some lattices or families of lattices can be reduced using SVP oracles in dimensions that are substantially smaller than the rank of the lattices n. So previous work include a lot of heuristic estimates, obviously, because BKZ works exactly by using these SVP oracles in smaller dimensions, as well as a recent result by Leo Ducas on dimension n/2 SVP oracles are enough to reduce the integer lattice. So our results include an extension of Leo's work, where we relax the approximate factors in the SVP oracles by a constant margin. And also for many NTRU instances, we show that n/2 is indeed sufficient to reduce the lattices. So this does not incur any security loss on lattice isomorphism or NTRU-based schemes. I'm only talking about provable results and not the heuristic results, which end up being better than what we can prove. All right, so I'll start with a few building blocks and reminders on lattice algorithms and SVP oracles, etc. So if you're given a lattice that has a sort of a skewed basis or a bad basis, lattice algorithms try to find short vectors in these lattices. So they try to make this basis a better basis, a shorter or a more orthogonal basis. So on the right here, I have this Gram-Schmidt profile. So if you're not familiar with this, I'm just plotting the norms of the Gram-Schmidt vectors. So here the first one is the norm of B1, and the second one will correspond to the norm of the projection of B2 orthogonally to B1. So you can see that this is very small here. And when I reduce the lattice, this becomes sort of horizontal. So if I can lower the slope of if I can make the profile more horizontal, then I'm reducing the lattice in a good way. All right, so first building block is SVP reduction or an SVP oracle. So SVP stands for the shortest vector problem. And the idea of this oracle is that I'm given a lattice that I represent here with its profile on the left. And I output a basis whose first Gram-Schmidt norm, B1 star, is reduced and it's minimized to become the shortest vector of my lattice. So I can also relax this oracle to a gamma SVP oracle, which only requires an approximation. So you can see that this loss in norm on the first vector is impacts the norm of the other vectors and makes the profile more horizontal. All right, so I'm going to consider two families of lattices. The first one is the hypercubic lattices, so the integer lattice and rotations thereof. So these are used in the lattice isomorphism problem, which itself is used to build the Hawk signature scheme. On the other side, I'm going to consider NTRU lattices, which have been introduced now more than 25 years ago. And so this has a lot of structure and is used in many schemes and standards. So NTRU, Falcon, etc. In general, it's quite a hard thing to estimate the security of these lattices. And so people at the time relied on low-dimensional experiments and now rely more on predictions of the behavior of certain lattice algorithms, so heuristic predictions for BKZ, for example. So the motivating question in this work is the following. Is it possible to provably solve SVP in special families of lattices of rank n by only using SVP oracles in dimensions alpha n, where alpha is less than 1? I'm talking asymptotically, so take the limit of your alpha. So what is known for hypercubic lattices? Recently, as I was saying, Ducas proved that alpha equals 1/2 is enough. However, for NTRU lattices, until now, no alpha better than 1 was known, but it was conjectured some almost 20 years ago by Gamma, Hargrave, Graham, and Yuan that alpha strictly less than 1 should be possible. All right, so another tool I need is duality. I won't delve into the mathematical details, but just think that every lattice lambda can be paired up with a dual lattice lambda dual, and every lattice basis of my of my lattice lambda can be paired up with a dual basis of the dual lattice lambda dual that satisfies this nice property, which is the first norm. So the norm of my first vector in the dual basis is equal to the inverse of the last Gram-Schmidt norm for the primal basis. And we have this nice observation here that hypercubic lattices, so Zn, this is isodual, it's equal to its own dual. All right, so with this, I can define the dual version of the primal reduction, which is essentially doing the same thing as before, but in the dual. So I'm converting my basis to a dual basis, reducing the dual basis, which makes D1 small, which in turn makes Bn star larger. And then I lose some norms and I get a more horizontal profile, which is good. I think this might be a typo. This should be the dual of the lattice. All right. So now that I have this, I can introduce the main framework for the algorithm that was used by Ducat and that we modify in our work. So this is an important slide. Consider this big square here to be the basis for a lattice lambda, and I'm going to keep lambda for the large lattice, the main notation. And consider these sublattices L and N, which are generated by the first k and k+1 vectors of my basis. And on the right, I've got the profile. And so for now, the volume of this lattice N is equal to the volume of L multiplied by this Gram-Schmidt norm bk+1. So that's the one in the middle of my Gram-Schmidt profile. So the primal dual reduction, or a variant of slide reduction, consists of two steps, which I will iteratively repeat. First one is applying SVP on a projected sublattice lambda quotiented by L. So you can see this as projecting lambda orthogonally to L. This is in dimension k+1, which is roughly a half of the dimension. And the effect of this is that bk+1, this pivot vector in the center, will be reduced in norm, and its norm will become the shortest vector of lambda quotiented by L. Now I can do the dual of this operation in N, and when I do this, the first dual Gram-Schmidt norm, so the last primal Gram-Schmidt norm, will be fixed like this. So this pivot will now increase. And the effect of repeating this operation is that I'm sort of pumping out the volume of the first half of my profile to the second half by iteratively relying on this pivot. So this is a known algorithm. And the advantage of this thing is that it's quite easy to analyze. So if I look at this at one primal dual step, then how does the volume of L, so the first k vectors, change? So after the primal step, we had this relation because bk+1 star is lambda1 of my projected sublattice. And after the dual step, we have this. So here L primed is the lattice generated by the first k vectors after my operation. And we can combine these two equations to obtain that the new volume for the sublattice generated by the first k vectors is decreased by this multiplicative factor, which is a product of two shortest vector norms. So now if this product is strictly less than 1, then we win, because we know that repeating this will decrease the volume until this volume is minimal. But for general lattices, we don't know much about a bound on this product. So the observation of Leo Ducat last year was that he can apply this to hypercubic lattices by relying on this this nice bound here. So if L is a sublattice of the integer lattice and its volume is not 1, so it's not just generated by the identity matrix, then the projection of the integer lattice onto orthogonally to L has a shortest vector whose norm is strictly less than 1. And we can have this bound. This is quite nice because it's much stronger than what you would get for random lattices or Minkowski's theorem. And this means that the volume of L, because you can also apply it to the dual bit of the equation, will decrease by at least 1 minus 1 over n multiplicatively at each step. And so this shows that you can use only n over 2 approximate oracles. So our first result is to extend this lemma and to show that if L is a sublattice of the integer lattice, such that L has no, instead of having volume greater than 1, it has no unit vectors, because if it has unit vectors, then we win. We've found the shortest vector in the lattice. Then this projected lattice has shortest vector less than something that's smaller than what the previous lemma was giving us. So if k is n over 2, then this says that the lambda 1 here is less than 1 over square root 2. So when I multiply two of these together, it means that I have leeway for square root 2 approximations. Also, square root 2 approximations can be used to check for unit vectors in a sublattice of the integer lattice. So this is what we do in our algorithm. We add this step here. We check for unit vectors in L. We then gamma SVP reduce the projected sublattice, which we've seen before, and do the same in the dual side. And so we can basically just relax the approximation factor. So why is this important? Or maybe I don't know. Why does this matter? Because the best provable anti-heuristic algorithms for the Z lattice isomorphism problem run in time 2 to the n over 2. It's also known that for large enough constants, dimension n over 2 gamma SVP runs in time that is strictly less than 0.5 in the exponent. So this asks a real question: what's the real practical cost of solving square root 2 SVP? And if this is less than 2 to the 0.5 n, then maybe we can break the n over 2 barrier in the exponent for lattice isomorphism problems. So this would be nice, but we don't really know. It's also a bit provocative to think that this is the easiest lattice and we don't really know how to efficiently reduce it. All right, so now for applications to the NTRU lattice, or some NTRU lattices. I go back to using exact SVP oracles, and I recall that using my primal dual reduction, the volume of L is multiplied by this quantity. So I have this quick lemma here, which is similar to the idea that we had before. So if the sublattice doesn't have a shortest vector of the entire lattice, then I show that and this is pretty straightforward, that the shortest vector in the projected sublattice is less than the shortest vector in lambda. So effectively, if I can test that the sublattice doesn't have a shortest vector using an SVP oracle in dimension n over 2, then at each step, the volume will be multiplied by at most lambda 1 of lambda. And because I can do the same thing on the dual side, times lambda 1 of lambda dual. So now the question is, does there exist lattices for which this quantity is less than 1? This sounds a bit strange, because if you take a random lattice, you would expect using some Gaussian heuristic or something, you would expect this quantity to be much larger, maybe square root n times square root n. So this is a bit surprising, but in fact, because of this self-duality that NTRU also kind of has. So NTRU is if we use this ring, it's when you rescale it, it becomes isodual. So you can compute the value of lambda 1 of the dual, and this gives you lambda 1 squared divided by q. So because lambda 1 has to be quite short in NTRU, and the modulus is sometimes quite big, we can look at practical instantiations of NTRU and variance and see that this product here is often less than 1. So this is the NIST submission for NTRU. And this also, so the gap you have with 1 allows for some leeway on the approximation factor that you then use. So the conclusion is that many NTRU instances are provably solvable with n over 2 SVP oracles only. All right, so just to finish, I'll compare this with what we know stick reduction to see how things compare. So asymptotically, I'm still looking at asymptotics here. File and behavior of random sublattices or subspaces in BKZ. So this gives something that's exactly the same in the case of the hypercubic lattice, which is surprising, I would say. And in the case of NTRU, we still have some difference. So I'm using some values for the asymptotics of Q and lambda 1, but this doesn't matter much. But this is still relatively close, and I think we help bridge this gap between theory and practice here. This also shows that, yeah, the non-uniqueness of the shortest vector is not directly relevant to the optimal block size. So this has been known for a while now, but in the past, people would just look at the gap between lambda 1 and lambda 2 and derive some estimates from that. I don't think this is the the good way to see things. So to conclude, like with the integer lattice, NTRU's geometry makes it easier to provably reduce. And we give an algorithm that uses only dimension n/2 SAP oracles. These oracles can be relaxed by a certain small constant gamma. And this reduces the gap between the provable and the heuristic results. All right, so, oops, sorry. So yeah, just bonus questions if I have a bit of time. It's a bit provocative maybe, but which of NTRU and lattice isomorphism is the easiest? I don't think there are sufficiently clear security estimates at the moment. It's a legitimate question. Can we exploit the ISO duality better than just using this artifact that the product of the lambda ones is less than 1? And can this be made practical, this primal dual reduction, especially with the case of the integer lattice where heuristics and theory are so close? All right, so the paper will be revised soon, and I thank you for your attention.
Do we have any questions? And also, if people have questions on Zoom, you can ask them.
Thank you for the lovely talk. So there's another class of random lattices that we somehow know vague isodual properties about, the uniform Curie lattices, right? And we also have probabilistic upper and lower bounds on the minima of these that are different from what Minkowski might naively tell us. So what, if anything, is an obstacle to using this kind of analysis in those cases?
Yeah, I guess a similar analysis would work. It only depends on this relation between the lambda one of the primal and the lambda one of the dual. But if you can stretch your Curie lattice enough, then yeah, this is probably applicable as well. But I haven't really looked at that. Cool.
Thank you.
Any other questions?
Yeah. Thanks for the talk. I was just wondering if Alexander's made dimension reduction for cutting dimensions in the when you're looking for recovering the private key in NTRU plays a hole here. Because you kind of could reduce the dimension of the lattice.
Yeah, so there's different ways to reduce the lattice, I guess. I haven't really looked. I'm not sure I understood your question fully, but maybe we can discuss it afterwards, or if you want to reiterate.
Yeah, just like when you're looking at for recovering the private key in the NTRU, you have the F component and the G component, right?
Yes.
So Alexander's main idea was to cut some of the coordinates of the G component, and you still have a lattice with a smaller dimension, let's say n plus k.
Yes.
And you could still recover the private key F.
Yeah. Okay. I think I see what you mean. So I think this is the analysis of this would be probabilistic, and it wouldn't really fit in the same provable framework. But I think this is sort of incorporated in the heuristic analysis of the attack. So sort of the natural thing that BKZ will do when it reduces the lattice is going to eliminate maybe if you have many zeros in your G, it's going to eliminate them naturally. And so it's going to sort of do the same thing as if you were projecting in the lower dimension and then applying your reduction.
If there are no more questions, let's thank Henry again.